Here we'll go over the practice pop quiz that we took earlier in the week. The numbers are all messed up just because when I made the quiz, I photocopied it directly from other practice problems that you guys have completed before. So in question number 2 here, what is the acceleration of a 70 kilogram mass being pulled by 140 Newton force? 140 N equals 70 kg times the acceleration, which will equal, when we divide 70 by both sides, we get 2 meters per second squared. On the Earth's surface, how much does a 100 kilogram mass weigh? Remember, mass is not weight. Weight is the force due to gravity. Force due to gravity is how much gravity pulls down on an object. Just like any force, you calculate the force by taking the mass times the acceleration due to gravity, and you now have 1,000 newtons. What force is necessary for a person to hold 50 kilogram mass over their head? We're just talking about holding it there. We're not talking about moving it or throwing it up. We are just talking about holding it above your head, which means we are supporting its weight. 50 kilograms times 10 meters per second squared, 500 newtons. How much force is required to accelerate a 10 kilogram mass upward? Upward always indicates that we're fighting gravity at a rate of 5 meters per second squared. So 10 times 10 plus 5. 10 times 15 equals 150 newtons. Another way to do that is 10 times 10 and 10 times 5 and add those two answers together. Remember that since we're talking about upwards, we need to not only counter the force of gravity, which is required just to hold the object in your arms, but then also account for the rate of acceleration that is desired, in this case 5 meters per second squared. So we need to account for the 10 for gravity and the 5 for the desirable rate of acceleration. A 50 kilogram rocket generates 990 newtons of thrust. What will its acceleration be if it is launched straight up? So, I like the diagram. 50 kg rocket, fire, wing, cone. If it's a 50 kilogram object, we need to account for force of gravity, F of g. We also need to account for force of rocket. So F of g is going to be 50 kilograms times the 10 meters per second due to gravity, 500 newtons of downward force. We're also talking about 990 of thrust, or the total force. So if the force of rocket is what we are solving for, we need to go 990 minus 500 equals 490, divided by the 10 meters per second squared, divided by the force divided by the mass will give us the acceleration. 490 divided by 50 kilograms is 9.8 meters per second squared is the upward rate of acceleration. Another way to solve this is taking 990 newtons of thrust and divide it by the 50 kilograms of the rocket's mass. We know that 990 divided by 50 gives us 19.8 meters per second squared. Now you should be thinking, wait a second, that's not the right answer. That's not 9.8 meters per second. It's 10 meters per second faster. And that should then send off a signal in your head, oh right, if we have just taken the thrust or the force and divided it by the mass, we have not yet accounted for the force of gravity, or in this case the acceleration due to gravity. Subtract 10 meters per second squared, and the answer we come out to is 9.8 meters per second squared. Oops. One way or another, however you solve this problem, if it's this way over here on the right, or if it's this way over here on the left, we must account for gravity in one way or another. We either do that by calculating the force due to gravity and subtracting it out of the equation, or we must account for the acceleration due to gravity and subtract that out of the equation. Either way, account for gravity. If the same rocket is launched from Mars, what will its acceleration be? So, we'll solve it first with accounting for the acceleration due to gravity. 990 divided by 50 kilograms equals 19.8 meters per second squared. Subtract the 4 meters per second squared on Mars, and you get 15.8 meters per second squared. Alternatively, you can take the 990 newtons of thrust and subtract the force due to gravity on Mars, which is going to be 4 times 50, or 200, which will get you 790 newtons of force acting on the 50 kilogram object, which gives you an answer of 15.8 meters per second squared. A 7 kilogram block rests on a surface with 6 newtons of friction and is being pushed by a 55 newton force. What's its acceleration? I again like to diagram. Here's our block. It is 7 kilograms. There is 6 newtons of friction, and there is a 55 newton push. 55 minus 6 equals 49 newtons divided by the 7 kilograms equals 7 meters per second squared. Remember, friction opposes motion, so friction is going to oppose the push that you apply to the box. So right here we've got this 10 kilogram hanging block. Multiply that by the rate of acceleration due to gravity. Why do we multiply it by the rate of acceleration due to gravity? Great question. Since it is hanging off of the table, the only force that is acting on it, other than the force of the string, if we cut that string, the only force acting on that block would be the force of gravity. If the force of gravity is acting on it, we know it will accelerate at 10 meters per second squared. 10 times 10, 100 newtons. That is its weight. That is its force of gravity. That 100 newtons, since it is attached by a string to the second block, that 100 newtons is also pulling on that 20 kilogram block. 100 newtons divided by 20 kg equals 5 meters per second squared. What is the mass of the block on the string if the acceleration of both blocks is 4.9 meters per second squared? Okay, so we're going to talk about how it's possible that both blocks accelerate at 4.9 meters per second squared and not 10 meters per second squared in a minute. But for now, let's just forget about the problem itself and just think mathematically. If this block, we know that it's going to accelerate at 4.9 meters per second squared, but we don't know its mass, so we can't do anything yet. We do know this block, though. It's going to accelerate at 4.9. 4.9 times 10 is going to be 49 newtons of force. 49 newtons of force is going to be equal to the mass times 4.9, right, because that force will also be acting on this block. Divide both sides by 4.9, and we get the mass equals 10 kg. Now, why or how would the acceleration only be 4.9 meters per second squared? The reason that that's possible is that we must assume that I guess there just has to be some friction going on there. It's not stated in the question. It's not even integral to this question that you understand that there is friction occurring. The reason that we're assuming that is because if the problem didn't say anything otherwise, we would know that this object here should accelerate at 10 meters per second squared. So in a world where we're back to the table with no friction, right? We've got this 10 kilogram block here that's attached to this question block here. If this is going to accelerate at 10 meters per second squared, and this one accelerates at 4.9 meters per second squared, that means that there's 49 newtons acting there, and this one, so 49N equals mass times 10. The mass would equal 4.9 kilograms. So that's why on one of the answer sheets, I think to problem set number 3, I put the answer as 4.9 kilograms. Technically, as number 16 is written, this is an incorrect answer. Because the question says, what is the mass of the block on the string above if the acceleration of both blocks is 4.9 meters per second squared? Here, we've assumed that it's actually going to fall at the rate of gravity because this is frictionless. No friction. However, if you're reading the question and you're going just by the question alone, that this one accelerates at 4.9 meters per second squared, the only way that would happen, the only way that the block would not just move at the acceleration due to gravity is if, excuse me, is if there was some friction between the 10 kilogram block and the table. Now, I've kind of gone off on a tangent here explaining how this is possible. You don't really need to understand that in order to solve the problem. However, it's important to understand, or it's helpful to understand, why this would be the case, that in this one instance, number 16, it's the only problem where we've talked about the hanging block not accelerating at 10 meters per second squared, but instead, in this case, accelerating at 4.9. It is important to understand that the reason that would happen is because of friction between the block and the table. Just to confirm, the answer key is down here.